presentation is about the quantum generative models for medical imaging. Basically, we aim to develop a synthetic data based on real data, and why synthetic data is important in healthcare and medicine. Uh, First, because we can have a scarcity in the data set. The challenge regarding the patient privacy, also the seamless data sharing, because we have a bureaucratic issues when we need to share between institutions. The data set robustness enrich the statistical variety in the training sets and also accelerate the innovation. The data set we chose for this project is a retina mist. It's images from the fundoscopy in the eye, where we can identify signs of diabetic retinopathy, like edema around of the optic nerve. We chose the resolution of 64 with the computational resource. And here we need to note that the images is colored, so it's the higher dimensionality. We used the 10% of the training data set to simulate data scarcity, because the real data set is over 1,000 images. We are using just the 10%. And when we have data scarcity and we are developing machine learning, we can have a overfit risk, obtain a poor generalization and unstable training. For this, we have some options like again, it's a game theoretical approach where two neural network compete against each other. Like we have a generator and the classical discriminator. And we have also the QCBM born machine. The QGAN we have a quantum generator and a classical discriminator, and the QCBM it's based on the born ruling measurements. So we need to put all the information, because it's a lot of information, especially because it's colored. We have the RGB, it's not just the grayscale. And one of the approach we are using here is the autoencoder, where we put compress the data into 8D vectors. And Dr. Laya shared with us this approach. We are also trying to apply this. It's a Q-pixel encoding, where we capture both pixel colors and the position into a single normalized quantum. And an advantage of this kind of encoding is 90% of the gate reduction. And the summary of the project is the implementation of QGAN and QCBM architecture to learn data distribution within a 8D latent space and evaluate model performance under data scarcity. We are planning to also using the 20 and 30% of the data, and also the privacy preserving. This is the first result we have obtained. It seems like the synthetic data, it's not feasible, but I was reading that even if it's not visually seems feasible, it can have information that we can, for example, associate with the real data and try to develop machine learning to see the performance. So right now, Avshek is gonna share more about what we have developed.
Thanks, Antonio. Am I audible?
Yes, you are.
Yeah.
Yes. Okay, thank you. So I specifically worked on the quantum circuit born machine approach for the same problem statement of generating synthetic images, basically. So as Antonio stated earlier, the way it works is that, based on existing distribution, probability distribution of data set, it could be of images, could be of any other data set. Basically, it tries to generate samples from that distribution, which kind of is approximately similar to the original distribution of the target images. That's the approach. And it typically works with a quantum circuit of different rotational gates and um, C0 gates for entanglement. And for this, so again, I had to use an encoder. So Dr. Lai, I took your advice and I removed the encoder, and the results were worse. I think we'll have to, at least for this problem statement, I think we'll have to explore QPixel properly and implement it to reduce the dimensionality. But with the autoencoder, with the latent space, the MSC loss got minimized, and the autoencoder images were fairly okay, which means it was able to keep most of the information intact, and that is what was used as the feed data for the qubits. So we had 8 qubits, one for each dimension of the latent space. And this is the layering we have. So it's a chain topology that we use, wherein we have different layers. It's a bit similar to your classical neural networks in the sense that there are different layers of quantum gates here. And the idea is here to basically optimize on the rotation angles, the theta, across the rotation gates across layers. And so as you can see, so there are 8 qubits, so there are 8 Hadamard gates, and which helps us create the superposition states. And then we have the rotational gates with these parameters, and we have the C0 gates for entanglement. And now, so what I've done is I've used Adam optimizer, which is the gradient-based optimizer, which has adaptive learning rate. So basically, with each um, change for different theta values, it basically adapts the learning rate on its own. And that way it's better in terms of avoiding local minimas compared to your gradient descent. And the other approach was to also use, maybe at some point I'll explore it, was to use a gradient-free approach, especially if I run it on a quantum hardware at some point, using something like a CMAES or PSO. And so if you could go to the next slide, Antonio. Yes, so all in all, so we had like 24 parameters, so different theta values that needed to be optimized. Next, please. So this is the set of images that got generated in for 10% data scarcity. This is what we had shared the data. So unfortunately, even when I increased the scarcity a little bit, I realized that the problem was that uh, enough information was not getting encoded for qubits. So there was a missing learning there in the very first step itself. So anything I was generating had problems with diversity in terms of images, plus the quality of images in terms of the pixels, pixel representations. So for the loss function, so I chose KL divergence method, which was, I think, invented way back in 1951. It's really popular along with MMD for minimizing losses on QCBM. So as you can see, we the loss got minimized, and to a certain extent after around 200 epochs, and this is the best loss that I could gain as part of the training, which, as per certain benchmarks that I've come across, is fairly optimal, which means that it is able to train. It's just that the data I trained on, again, going back to that point, is not informative to begin with. It didn't have all the patterns that we're looking for to have enough diversity and quality compared to the original target you know uh, distribution that we started with. So if you could go back, so if you see the diversity and quality scores are a bit low. Next screen. Thank you. So there are a couple of approaches. I was reading about it. in the last few days, and one is QPixel, which I think uh, probably kind of supersedes even FRQI or even improved FRQI as per the paper that Dr. Leah shared. And we'll be working on using that to encode the images efficiently using qubits. And few other things that Dr. Leah suggested was that we start with a higher scarcity. But I think once we solve the encoding part, we can then see an actual difference once we start with 50% or even beyond that, and then gradually bring it down to see if there is any degradation in quality of the and the diversity of the images that we generate. And then parallelly, I also tried a stable diffusion model in the same diversity, but unfortunately, it didn't work out. The images were horrible. So I was using, it basically got trained, but there was a lot of difference in terms of similarity scores between the original and the stable diffusion images, and it was extremely slow on 10% again. The sample was very limited. I think well, I'll explore a few other classical options for the same set of data scarcity percentages, 10, 20, and 50, and then we'll compare it with our QGAN and QCBM models and get back definitely on the output. Thank you again, Dr. Leon.